This is chapter 10 on approximation methods of a mathematical physics course called Quantum Mechanics at senior level. The first author of the text used for this course is Davies, two authors, Paul Davies and David Betts, and the book is just called Quantum Mechanics and second edition. Now, if you want to get this book for free, you can download it electronically from the internet on emule.com, emule.com, get it for free. Or if you prefer a hard copy, and a lot of people do, there's a certain convenience to having this rather than a rather heavy iPad, unless you got the more recent versions. I have an iPad, but it's the first version. It's clunky and heavy, so I still prefer the paperback, but that'll change. Okay, so to get details about the course, its chapter headings, stuff like that, go to my website. So Prof. Hugo deGaris, Professor Hugo deGaris, my name, Hugo personal name, deGaris family name, .wordpress.com, and there are various tabs. Click on the deGarisMPC tab, M for mathematics, pure mathematics, P for physics, so mathematical physics, and C for computing. About 10% of the courses will be on theory of computation, which in fact will be my next course, the third that I'll be giving. This course is the second. We're finishing off now. It's chapter 10, and let me just check. I think in the text, there's only one more chapter after this one. So after chapter 11, we'll finish this senior level undergrad course on quantum mechanics, and then move on to computer theory. Right? Well, basic idea of this chapter is that in practice, when if you're a real quantum mechanic, the person, it's unusual to have a physical situation that you're studying quantum mechanically where the solutions are exact. You can write down non-approximate solutions. You have definite terms like exponentials and cosines and whatever. So that kind of case is relatively rare. In most cases, you'll need to make approximations. You'll need to solve numerically using computers. So that's the norm. So this chapter is more applied in a sense. It's facing up to the reality more, because very few problems have exact solutions. So now there are two in this chapter. We'll deal with two approximation techniques. The first one is called perturbation theory. So you're perturbing something. You're gently nudging it, disturbing it somewhat, and I'll explain what that means in more detail in the coming sessions. And the second approximation technique is called variational methods, and we'll do that. Not even on this board. It'll be several sessions away. Okay. So what's perturbation theory? Well, it's often the case that there are lots of problems which are very close to a problem that is fully solvable, with exact solutions, but with just slight differences. So the basic idea of perturbation theory is that you perturb, in other words, modify or change or disturb a little that problem that is that does have exact solutions, and then you tweak it, you modify it slightly. And in practice, what does that mean? It usually means you take the problem that you're concerned with. You notice that it's very similar to some other problem that does have exact solutions with its own Hamiltonian. Call that exact solution problem Hamiltonian H naught, right? H hat naught, the little zero, sort of like the basis that you'll be modifying to be able to deal with the problem that you're really interested in. Okay, so to perturb in this sense means to basically just add a small term, a correcting term if you like, to the basic Hamiltonian, to your H hat 0. Remember H hat 0, that's the Hamiltonian for a problem which has exact solutions, usually. Okay, so now the way perturbation theory is done is it uses a parameter, just called lambda, and it's a kind of correction term. Now this won't be clear until we get into the details in the next few sessions, but I'll try sort of in a hand wavy way give you, an idea of what's involved. You make a correction to the Hamiltonian you're talking about. You add a small term. In fact, it'll be H hat 0 plus lambda H hat dashed, and the H dashed, that's your corrected Hamiltonian. And you'll let the lambda value, it's just a constant, right? And you'll let it have a value between 0 and 1, let's say. Now, the actual results you get, like the corrections in the energies and the eigenenergies, and the so-called energy eigenvalues, and the energy eigenfunctions, U, they too get corrected. They too have these lambda terms added to them. So now I'm being a bit vague, but it'll become clear in a while, and you'll correct or modify or perturb, hence perturbation theory. You'll perturb like three things: the Hamiltonian. So you'll have something like H0 plus lambda H1 plus lambda squared H2 ... Similarly with the eigenvalues. So you'll have we're talking Hamiltonian. We're talking energy. Remember, the Hamiltonian is the name of an energy operator. So its eigenvalues will be energies, allowed energies, discrete, quantized energies. So your corrected or perturbed energy eigenvalues will be of the form E0 plus lambda E1 plus lambda squared E2 ... Okay? And the eigenfunctions, similarly, they'll be of the form U0 plus lambda U1 plus lambda squared U2 ... And so you're having your Hamiltonian, your eigenfunctions and your eigenvalues. They're all power expansions in terms, well, they're expansions in powers of lambda, right? Lambda and then lambda squared and so on. And you'll plug these terms, these corrected terms, these perturbed terms, into your eigenequation, and then you will equate powers of lambda, the coefficients of lambda. And you'll have an equation where the right-hand side is 0, and that means that all these coefficients of powers of lambda individually have to be 0. So the right-hand side is also 0. And that allows you to derive relationships between, you can find formula for like E1, the so-called first-order correction to the eigenenergies, stuff like that. And U1, which is the first-order correction to the eigenfunction due to this perturbing the extra term that you add to the Hamiltonian, stuff like this. Now, you might be a bit confused at the moment, but it's not too difficult. It'll become clear as we get into later sessions. All right. So here's sort of what I've been saying. So you start with a basic Hamiltonian. So that's why you put this little 0 down here to indicate it, that it's the start, your starting Hamiltonian, your basic Hamiltonian. Right? And the 0 up here for the eigenfunctions, they're in a sense your basic or starting eigenfunctions, and similarly with the eigenvalues, the eigenenergies in this case. So here in a sense you could say this is your basic eigenequation, right? With your three things, your operator, your basic operator, your basic eigenfunctions, and your basic eigenenergies, your eigenvalues. And the zeros here, they tell you that they're your starting functions or values or operator. Okay. Now, what you do then is you add a term to your Hamiltonian, and this is the perturbing or disturbing, if you like, Hamiltonian. It's usually a small correction relative to this one. Like, how can I put this? If you're talking energies, for example, the eigenvalues of this one would be large in comparison to the changes in the eigenenergy due to the correction. So the energy changes, if you like, to the eigenvalues will be small in comparison to the eigenenergies of this Hamiltonian. Right? So it's a perturbation, it's like a small disturbance. And hopefully your basic Hamiltonian, your H0, that's the Hamiltonian for some system that hopefully has exact solutions. Because if you do have exact solutions, it makes life so much easier. You don't have to use numerical methods, approximation methods for solving this. All right. Okay. Now we're going to correct this a little bit. Now come down here. Now we're starting to use this lambda parameter. It's dimensionless. Just think of it as a constant, and let it have a value between 0 and 1. Now the actual formula that we'll derive, the correction terms, like for example, what's the change in the eigenenergies? The delta E. All these formulas that you derive, and what will the change in the eigenfunctions be? You can express them in terms of a power series of lambda. I'll show you how to do that next session. And but the actual results that you get, the corrections in the energy, the corrections in the eigenfunctions, they do not involve the lambda. But you found those terms, those formula for corrections of the eigenenergy, the eigenfunctions, by using this lambda, and you'll see how that's done next session. Right? So recapping a little, you take your three things, your operator, those Hamiltonian, the eigenfunctions and the eigenenergies. So there's three things. You expand them in terms of a power series in lambda, and you plug all those terms into the eigenequation, something of this form, and from that you can derive expressions for the corrections, the delta E and the change in the eigenfunctions and so on, using this power series expansion with lambda. Now that will become clearer next session as we actually do it.